Hello lovers of chemistry, it's Igor, welcome back to my channel. Today, I want to shed light on the synthesis route of two fascinating natural products, Glauconic and Glaucanic acid. The only difference between these two structures is the presence of a hydroxyl group in glauconic acid, which makes the synthesis pathway slightly different in the final steps. These two structures belong to a class of polyketide-based natural product known as Maleidrides, which are isolated from filamentous fungi. They are characterized by at least one maleic anhydride moiety fused to a central medium-sized carbocyclic core, a key feature of this natural product family. Based on the number of carbon atoms in the central ring, Maleidrides are classified into nonhydrides, octahydrides, and heptadrides. The core structure of these compounds is formed through the dimerization of two monomers units, which leads to diverse regioisomers depending on how the monomers couple. The possible dimerization modes include head-to-head, head-to-tail, and head-to-side couplings, resulting in Maleidrides core with different substitution patterns. As you can see, Glauconic and Glaucanic acid fall into the category of nonhydrides due to their 9-membered ring central skeleton. They were first isolated in 1930 by Weichmann from Penicillium glucam. Later, many members of the Maleidrides family were found to exhibit promising biological activities, making them valuable for development of novel pharmaceuticals and agrochemicals. For example, rubrotoxin A inhibits protein phosphatase 2A and suppresses cancer metastasis. Cornexistin exhibits significant post-emergence herbicidal activity against a wide range of monocotyledonous plants, while remaining selective for corn. Despite their biological activity and unique structural features, the reported synthesis route for Maleidrides remain very limited. The Thomas Magauer group, known for its work on the total synthesis of polyketide-based natural products, has made significant progress in this field. In 2020, they successfully synthesized cornexitine in quantities exceeding 100 mg. More recently, the group introduced a novel asymmetric approach for synthesizing glauconic and glaucanic acid, which is the focus of this video. I also made a video about the total synthesis of gonoplanine, another polyketide synthesized by the Magauer group. Check it out if you are interested in the synthesis of this amazing structure. Now let's analyze the retrosynthetic pathway. Two cyclic anhydrides are unstable, so the group preferred to install them at the latest stage of the synthesis. One of the cyclic anhydrides is masked as a furan, while the other is derived from the ketoester via a trifylation carbonylation sequence. This intermediate can be simplified by removing the methyl group and disconnecting the carbon-carbon bond. The ephenyl substituent can be installed on this compound via an asymmetric Michael addition, and a bond-free dicarbonyl system can be generated through the Claisen Condensation. The double bond can be produced using a Wittig reaction, and breaking this carbon-carbon bond gives us the oxazolidinone building block and the aldehyde. The carbon-carbon bond can then be formed through a syn-Evans aldol reaction. Now let's go through the forward synthesis. In the first step, the aldehyde and oxazolidinone need join together through an enantioselective aldol reaction. The Magauer group used the Evans chiral auxiliary to install both the ethynyl and the alcohol substituent on this intermediate with syn selectivity. In other words, only one phase of the aldehyde is attacked by the enolate. Notice that using commercially available dibutyl boron trifolate gave diastereomeric mixture of aldol product, so the less common dicyclohexyl boron trifolate was used in the reaction. But how does it actually work? Let's break down the asymmetric addition in this reaction. Firstly, the presence of boron trifolates results in the corresponding enolates. After that, the enolate selectively attacks one phase of the aldehyde. This reaction proceeds through a Che-like transition state. Notice that the boron enolate adopts a Z conformation in which the ethynyl substituent is located in the axial position. On the other side of the double bond, you can see the 5-membered ring heterocycle in the axial position, with the benzyl substituent directed away from the center of the ring to reduce steric hindrance. The boron atom is attached to two oxygen atoms, one from the enolate and another from the aldehyde. The two cyclohexyl substituents occupy axial and equatorial positions. To simplify, I've indicated these bulky groups with purple spheres. The furan moiety of the aldehyde is also shown with a green sphere. But why is this transition state stable? This is because the orientation of the dipole moment of the oxazolidinol carbonyl group is opposed to the enolate oxygen dipole, which reduces the dipole moment of the entire transition state and leads to destabilization. This is an important factor for the facial selectivity of the reaction. Notice that if the other face of the aldehyde were attacked by the enolate, a bond-free diaxial interaction between the aldehyde substitution and the cyclohexyl group would destabilize the transition state. Now you completely understand the process of inducing chirality. If you are interested in such fascinating asymmetric reactions, which are often hard to imagine, check out this video where I describe an excellent example of an enantioselective reaction. In the next step, the resulting alcohol is protected with TBS and the oxazolidinol auxiliary is cleaved using lithium ethyl thiolate, followed by reduction of the intermediate thioester with diol. This protocol is used to prevent over-reduction and allows for controlled reduction to produce the aldehyde. Next, the Michael acceptor is installed on the molecule via a Wittig reaction, setting the stage for a 1,4 Michael addition. At this stage, the second ethynyl substituent must be introduced in an enantioselective manner. For this purpose, tall binap with copper iodide is used as a chiral catalyst. Note that a side product arises from the over-alkylation via a 1,2 addition of ethynyl magnesium. Subsequently, treatment of this intermediate with third butyl acetate triggers a Claisen condensation, producing a beta ketoester. In the next step, the primary alcohol is deprotected using a hydrogen fluoride pyridine complex, setting the stage for bromination under Appel conditions. Now it's time to construct the core 9-membered ring. The intramolecular cyclization proceeds upon the addition of potassium carbonate. To avoid intermolecular cyclization, the reaction is carried out under high dilution. Note that O-alkylation can also occur during the cyclization, but it remains a minor side product. After cyclization, a methyl group was installed on the molecule using LHMDS as a base and methyl iodide. This reaction led to the formation of two epimers, differing in the orientation of the methyl group. However, the group were unable to assign the stereochemistry of the newly formed stereocenter, because the product was not suitable for single crystal analysis, and no NMR data were ambiguous. Therefore, they decided to continue with the major product, hoping to determine its configuration at a later stage of the synthesis. For installation of the first anhydride moiety, this intermediate was converted into the vinyl triflate using KHMDS and Cummins reagent. A palladium-catalyzed carbonylation reaction was then performed to yield the corresponding carboxylic acid. At this stage, no NMR data of the carboxylic acid indicated that the orientation of the methyl group was opposite to that of the desired product. Despite the incorrect stereochemistry, the group proceeded with the installation of the two cyclic anhydrides. Treating the carboxylic acid with TFAA led to the formation of a cyclic anhydride. However, it was highly unstable to chromatographic purification. Additionally, all attempts to oxidize the furan to generate the second cyclic anhydride resulted in decomposition. Consequently, they decided to install the methyl group earlier in the synthesis, before the cyclization step. This crucial methyl group was introduced during the Claisen condensation step, using third butyl propionate, which contains an additional methyl group compared to third butyl acetate. All subsequent steps remain the same as previously described. Surprisingly, adding the base during the cyclization step led to the formation of the desired product with excellent diastereoselectivity, without producing the undesired epimer. But what is the origin of this diastereoselectivity? Let's take a look at the transition state. Calculation indicated that this conformation is the most stable among all possible structures. In this conformer, the double bond of the enolates adopt a Z conformation. Additionally, the S-cis conformer is preferred over the S-trans form. In this conformation, the potassium ion effectively interacts with two oxygen atoms, creating a rigid structure that sets the stage for the enolate to attack the carbon atom bearing the bromide. As a result, only the desired product is formed with high diastereoselectivity. If you are interested in complex total synthesis with fully described transition states, check out this playlist where I break down several fascinating total syntheses. With this cyclic intermediate in hand, we can now complete the synthesis of our target molecules. For the synthesis of glauconic acid, the first anhydride is installed by converting the carbonyl group to a vinyl triflate using phenyl-based triphenylmide. Treatment of this vinyl triflate with the palladium complex and carbon monoxide produces a cyclic anhydride and a carboxylic acid, which can then be converted to an anhydride using TFAA. Next, the second anhydride is unmasked by treatment with Jones reagent, and the target molecule is obtained by deprotection of the alcohol using Olah reagent. For the synthesis of glauconic acid, the group decided to remove the hydroxyl group from its intermediate by first deprotecting of the alcohol, followed by treatment with trifluoroacetic acid and a triethylsilane. After conversion to a vinyl triflate, the carbonylation reaction afforded the anhydride in only 25% yield, as an inseparable 8:1 mixture of epimers. Finally, glauconic acid was obtained by unmasking the cyclic anhydride.